Hello everyone. Can you hear me? Can anyone confirm?
Yes, ma'am.
Have you guys watched this week's lecture? Can you see my screen?
Yes, ma'am.
Okay. So in this week's lecture, we have moved on from the traditional image processing techniques to starting to use with an introduction to how deep learning methods will be used in learning problems. So the very first learning algorithm that people came up with was the Perceptron algorithm. So what does the So this algorithm actually says, given that my data is linearly separable, then I can always find a linear classifier that can separate them. So how this works is, it's defined by a simple linear classifier, that is say my input so I have inputs. My input vector is of dimension x1 to xn. Then I'll have weights corresponding to each of them that go as input to my perceptron, and I'll have a bias, so I get an output y. So this y is actually summation wi xi. I goes from 1 to n plus b. So this is usually written in an augmented form where so instead of doing this, I use another w that goes from w1 to wn with a 1, and I augment my input as well, x1 to xn. This is b and this is 1. So in that case, I can write this as w transpose x. So a classifier here is implemented as given x, my classifier will simply be sign of W transpose X. So if it is greater than 0, then I will assign it as 1. If it is less than 0, I'll assign it as 0. So this is a simple perceptron. So here what is our objective? Our objective is to learn W that can separate the two classes, right? So what they do is, I given my data samples, I at each time instant I'll be given with some samples, x of 1, x of 2, x of 3 and so on. So given this, I would want to and say W is randomly initialized, and I want to correct my W such that these two samples are separated. So the algorithm says, so at every step if W of k is my weight at the current instant k, then this plus I want to adapt it with some delta, so that delta can be so say if my sample is correctly classified, then I would not want to correct it. My weight is alright, right? So in that case I will not change it. So it is 0 if x of k is correctly classified. But say if my x of k belongs to class 0, and if my algorithm returns my h of x predicts it as class 1. So in such case I would want to so the delta k used is minus x of k and plus x of k if x of k belongs to class 1 and my algorithm predicts it as class 0. So this is the weight update equation. But why should this work actually? Why will it help correct your weights? Anyone wants to take a guess of why this should work in separating your two classes? How many of you have watched this week's lecture? Any of you?
No, I was not able to watch it. Was keeping it for the weekend.
Okay.
Had some work issues.
Okay. I would suggest all of you to try watching at least the first, the start of the week's lecture at least by Friday, right? Otherwise, I'll have to discuss what is taught in the lecture itself, and not really any new set of problems or anything if people have not watched. So try to watch the first part of the week's lecture at least from now on. So this is actually discussed in the lecture, but I will briefly go over it here. So what happens here is now say suppose I consider this case when my sample belongs to class 1, but my algorithm predicts it as class 0. So when it predicts it as class 0, that is my h of x is W transpose x is actually less than 0. So that is what my y, I'll write it as y. So y of x is less than 0, right? That is what my algorithm is giving. But I would want it to go to W transpose x should be greater than 0 to make the correct prediction. So if I correct it in this form where W of k plus 1 is W of k plus, so my delta W is plus x of k, right? In this algorithm, so plus x of k. Now if I with the new weight, if I calculate my output y at k plus 1 of x, that is w of k plus 1 transpose x of k, right? So what is this? This is w of k, current weight, the previous step, plus x of k transpose x of k. So this is so this term here is always greater than or equal to 0, right? So this was my previous prediction, y at k time step of x. So my yk plus 1 of x is always greater than or equal to yk of x. So that means earlier what was less than 0, I'm trying to increase that value so that I'll push it toward to cross 0. So this helps correct my that sample x of k here. In a similar fashion, whenever my sample belongs to class 0 and algorithm predicts it as class 1, there I am doing w of k plus 1 is equal to w of k minus x of k. So here I am actually trying to decrease the score, that is my inner product between the new weight and the sample. So w of k plus 1 transpose x of k here will be lesser than w of k transpose x of k. Same way here I'll have the negative term. So similarly here I'm trying to reduce my score so that it gets classified into class 0. How does this look? Say suppose my in a two-dimensional space, so say I have one set of data points here and another set of data points here. So here ideally there exists a linear classifier that can classify both of them separately, right? We are assuming they're linearly separable. So in this case, suppose my current weight is something like this. So the direction of this, so this weight vector is represented by this, in this direction. This is my w of k, and so this sample is misclassified here, right? Say this is the sample this is x of k and this is misclassified. Now I use this to correct my weight, right? So my w of, say this is class 1 and class 0. So this is misclassified into class 0 and I do w of k plus 1 is w of k plus x of k. So geometrically what I am doing is I am adding this weight vector here. So w of k plus x of k. So my new weight vector comes somewhere like this. So this will be w of k plus 1. So and the decision boundary with respect to the new weight would be something like this. So here I'm correcting it and I'm learning to separate them, right? So geometrically this is what is happening in a perceptron learning algorithm. But here just because I corrected this sample does not mean that all samples are correctly classified. So there could be some other sample, say I have a sample here, somewhere here, then it might misclassify a sample from the other class as well when I shift it. So at every step I try to correct its weight, but
In terms of CNN, can we say this is learning rate, like something working like a learning rate?
this is the direction of which, so x of k is the direction in which I am moving here. But so learning rate actually decides how much I will move in that direction. In the same algorithm, if I do w of k plus some eta into x of k, So this eta acts as a learning rate. That means in this
Okay.
direction I want to shift it, but to what extent I
How
want to
many
shift
units?
can be controlled by eta. So simplest algorithm which was initially proposed was just to use the sample itself as is. But so there are multiple variants of this. So you can use this, and instead of visiting one sample at a time, samples can be given in a batch. So in such cases I will get w of k plus summation over x of some x case. Say I'm given in batches of 10 at a time. So in that case what happens is I will look at all samples that were that satisfy this criteria. That is, it was its true it was label is class 1, but it was misclassified as class 0. So of this 10 samples, say I have 4 samples that were misclassified. In such cases I will use all the 4 samples here to update my weight. So this is the batch version of this perceptron learning algorithm. So I'll have, say I'll index xi by its, so I have x1 to x10. Say suppose x2, x4, x5, x6 are misclassified. In such case I will use all 4 samples to update it at once. So but it's all the same because I visit these one at a time or in a batch. At the end I'm still shifting my w by the extent of x, right? So these are equivalent algorithms, but it depends on how I give my data, how I want to update it.
Okay. Thank you.
So given that my data is linearly separable, there's a convergence proof on perceptron learning algorithm that shows that at the end, even though at each time step I can't guarantee that all of them are classified. In a finite, because my data, the number of samples is finite here. So that perceptron learning algorithm shows that in a finite number of steps, I will converge to a linear classifier that separates both of them. So that proof is a little more involved, which is beyond the scope of what we do here. Yeah. So, but then are these classifiers? So this is a simple linear classifier, but is this always sufficient to solve anything for any classification?
This will just show us the error percentage, right?
What? I didn't understand.
It will only show it will classify certain elements, and then there are certain elements which are not properly classified, right? So we can try other methods.
So here there is a very big assumption here. We are assuming the data is linearly separable, but in general data won't be linearly separable, and there's no guarantee that it will converge. So that convergence proof applies only when it's linearly separable. So in such cases eventually I might get the best but so what happens when the data is not linearly separable is this line keeps toggling, hovering around some weight, because at every instant it will try to correct one sample and it will misclassify something else, so it will never be able to classify them, right? Because if a line does not exist that can separate both of them, whatever you do, you can never separate. So that function of, a linear function can never separate it. So it does not, we can't always use linear classifiers. So a simple case when linear classifier can fail is, suppose my data points are, so I have, so I have one sample here, say pink is one classifier, and then this green. These belong to, so these are two classes I have. These two dots belong to one class, and these two classes belong to one other class. So is there a line that can separate these two classes? That's all I have. 2 samples per class. These are my 2 samples, and I want to separate them. So if I use perceptron learning algorithm, will it work?
No, ma'am.
No, right? There is no line. Whichever direction I pick, I can never be able to classify both of them, right? However you pick. So in such cases, linear classifier does not, and in general we don't know if the data is linearly separable or not. Most. So this is why to model a much richer class of functions, so the function which I choose as a classifier should be very rich, so that it can handle all sorts of possibilities in data. So that is where neural networks come in. So if I include nonlinearities in my this function class, it can model. So there's a, so when we use neural networks, so it's basically a sequence of layers where each layer has a certain number of perceptron units. So say this is my input, say x1, x2 to xn. So x is my input vector. Then so in neural networks you often have multiple hidden layers. So hidden layers is to so in perceptron what do we do? If my input directly goes to the output layer, and that can't, so that function is not rich enough to model this data here, right? So there's actually a proof that says if I include if my input belongs to dimension not apparent. If my inputs x1 to xn take zeros and ones only, like x1 goes to either 0 or 1, x2 is so binary. If my inputs are binary vectors, in such cases, if I have 2 to the power n nodes in hidden layer, I can represent any class of function and always try to classify them. So whatever values this takes in the two classes, this function hidden using one hidden layer with these many nodes at max, it can always identify a function that can separate both of the inputs. So basically using one hidden layer, sufficient number of nodes in the hidden layer, you can model any complex data distribution. So in reality we our inputs have very high dimensions, right? Say suppose in our if we take an image, even if we take a super so 100 using 100 cross 100, it is a very small image, right? But then if I flatten this vector, that would be 10,000 dimensional vector, which is very huge, right? So if I want to use my image as input and learn a classifier that can separate them, so the function which will be required to actually be able to consider all combinations in this 10,000 dimensional vector should be very complex. That is where neural networks are used extensively. But then, so when I use this, one thing is here, although I include multiple layers, if I simply have a linear function, that means say w1 transpose x. So say w1 is the weight vector for the first neuron, and w2 transpose x. So wn transpose x, something like this here, and then I simply pass it ahead using one more say w1 second layer transpose x, something like this. So if I simply use linear functions and model multiple layers, will I actually be able to model complex functions or not? Lots of layers, but all of them are just linear functions, one after the other.
In the above example you gave, where 2 points we are, it's impossible to do it. I think still it won't be possible, right?
Yes, that is right. So what happens is, even though if I include multiple layers, If all of them are simply linear, say this is Z1, okay, this has to be Z1, all this, the output at this stage, so so these are the outputs at my from this first layer, okay, and this goes into my second layer. Then what I simply have another weight that will act over this, right? So that's like another weight I'll use, W2 transpose into W1 transpose X. That's all. But then this is simply another matrix only. I can write it effectively as another W21 transpose X. So it's still a linear function. So the class of functions I am looking at is still linear. So it doesn't matter how many layers even though I include 100 layers, it's still a linear function. It reduces to. That means I'm not actually introduce anything more complex here, right? So that is where these activation functions are being used. That is, I will introduce non-linearities in between. So after say Z1 is my first neuron in the hidden layer, I will use some function f of W transpose X. So this f is nonlinear. So in this case, when I give Z1, Z2, Zm to my second layer, so that is a much richer function, right? Because I am introducing so many non-linearities. Some typical classical nonlinear functions that are used are sigmoid function. So a sigmoid function is given by 1 plus e power minus x. So this function goes from looks something like this. This is 0.5, 0 and 1. It peaks at this. So this is like a soft approximation of hard thresholding. So earlier in my perceptron algorithm, I only cared whether it crosses 0 or not, right? So so the function I was using was this. If it crosses 0, I'll put it to 1. If it doesn't cross 0, then it's this. So this is a soft approximation of hard thresholding. So ReLU is another nonlinearity which is commonly used. So ReLU looks like this. So it is given by max of 0 comma x. Now given, so I use a sequence of hidden layers, and after each neuron I have one such nonlinear activation functions. This models a very rich class of functions that can pretty much learn any data distribution. How do we learn them? We need to learn all WIs, right? The weights. How many of you have heard about backpropagation algorithm? So neural networks are learned through this backpropagation algorithm. So it is basically applying chain rule of derivatives. Say suppose let me so what are the costs with which I can I need to measure error in my output and actual label, right? So this is usually measured using error functions, or what we also call them as cost functions. So suppose this is my final layer. say I call this as layer L, and I'm getting some output. This is YL. So one standard error function which people can use is the mean square error loss. That is, I'll use summation minus say this is my desired output. This is my output from the network. So I measure the mean square error and I have capital in samples. So this is one standard way to measure loss. Now I know this is my error at the last layer, right? Here. So I will be able to compute so I would want to update these weights based on the error at my final output layer, right? So I need so what I want for any wij, so this is the gradient descent algorithm. In order to update them, I need to calculate this gradients, right? For each, with respect to each weight in the entire network. So how do I calculate them? So by gradient descent, what we are trying to achieve is if so each of these weights actually contribute towards error for the final output, right? So based on this, I will backpropagate my errors to each of these weights. That is, so the principle is somewhat like this. So if I shift my delta w by some delta w, then I will have the cost function also will shift by some delta j, and I want to minimize this. So I will choose the direction in which j is reducing and find the corresponding delta w that will cause that delta j. So by doing this,
Does changing weight in one of the layer affect the other layer, the upcoming layers as well? Like if W1 is the way the values are changed by delta something, will the W2 weight will also automatically change because it depends on the previous this thing?
yes, it does. So if I am in layer L, so my output I will compute this. Okay, let me draw this. Say this is layer L, and these are my neurons in layer L plus 1. So this is something like 2, 1. Say here I have NL nodes and here I have NL plus 1 nodes. So this is W NL to the first node, right? And this will further go ahead. So any change in input from here will affect my output of the node in my next layer, right?
Yeah.
So when I am backpropagating also, if there is some change coming in this direction, that change will be equally distributed among all of this.
Okay.
So each of this delta will affect my output at this node. That means when I want to minimize, if I want to minimize some error, I will have to update each of these, right? Because all of these affect my output. So
Okay.
so here I am say at this step, let me say this is some W11 of, let me write this a W11 of L plus 1. This is layer L. Are these notations clear? It looks very messed up, I'm sorry. So I'm indexing the superscript indicates the layer index and which connection goes to which connection. This is the first node, second node to first node. So that is W21, WNL to 1. So suppose my gradient dou-g, this is my cost function, right? This with respect to W11 of L plus 1. So this is the gradient which I'm getting to update this weight, okay? Now this, so what are all the inputs that so what are all the weights that get affected by this? Also remember, this is this in this layer, what are the total number of weights I have? Anyone? So there are NL nodes here, NL plus 1 nodes here. So what are the total number of weights I need to connect all the nodes from this layer to the second layer?
Like it must be the same value, right?
Same as what?
Number of layers.
NL into NL plus 1.
Right. So NL into NL plus 1. Because for each node, for the first node, I need NL number of weights, right? So that is my so W11, W212,
Okay,
W
got it.
NL1. So these many nodes I need to update just one node in my next output. So in total I need these many weights. But when I have this gradient, that is with respect to the weight of the first output neuron only. So what are the weights in this layer that it will affect? So let me say this weight can be written as some matrix here, right? So NL cross NL plus 1. So these are the number of weights I have in this so let this be of dimension 1 cross NL. So these are the neuron these are the weights that will take me from my input to my first so in my L plus 1th layer, the output of the first node in L plus 1th layer is affected by only W1 transpose, not the rest of the weights. Do you understand the structure of this matrix? Anyone confirm?
Yes, ma'am.
Yes, ma'am.
So what I am actually doing is to get my new vector output at layer L plus 1, I am multiplying this with uh, Z at L. Why am I writing this as Z? Why is it not Y? What is the difference?
It's W into X plus the bias.
X plus the bias is one thing, and also so ZL is actually f of YL. That is this is the activation I'm using. I want to apply nonlinearities at the end of each neuron, right? So ZL is so YL is the output of each neuron, that is W transpose X previous one, right? So this is what I want to do. Make sense?
Yes.
Okay. So what I wanted to tell is, so this is again the dimension of, what is the dimension of this vector, and this vector? So this is n L plus 1 cross nl, right? So what should be the dimension of this and this? So this is the outputs I am getting from layer L, right? So ZL has ZL0, ZL1 to ZLNL. So each of this corresponds to one neuron's output. Similarly, I get Y. So after I get YL plus 1, I'll again apply this activation. ZL plus 1 is given by f of YL plus 1, and so on. These are the steps I have. So at first step, that is, I can take it as Y naught is actually equal to the X vectors, X1 to something Xk. Then I pass it through a weight matrix. Let me represent the first all the connections from 0th layer, that is from the input to the first layer, as W1 Y0. So this will be Y1. Then I get Z1 as f of Y1. Then I pass it through another W into Z1. I get Y2. Then I get Z2 as f of Y2. So the dimension of okay, let me write this as n naught. So W1 will be of dimension n naught cross n1. W2 will be of dimension n1 cross n2, and so on. So this is the number of nodes in my input, right? N naught dimension. So n1 is the number of nodes in my first layer, n2 is the number of nodes in my second layer. So this is how the forward pass in neural network is computed. This is what we call as forward pass. And at the end I will have some Zn, Zf capital L, say this is my last layer, equal to f of YL. So this is what I have at the end, and over which I will compute my loss. I don't know if I messed up the equal to 1 to n. So ZL is my output. So DL is what I want, ground. This is what we refer to as ground truth. This is the output of last layer. So in backpropagation, what I do is I do go stepwise backwards and see. So from here, with respect to Z, I can compute the gradient, right? Dou J by dou ZL I can compute using this equation. So what is dou J by dou Z here? It will be 1 by 2 summation I is equal to 1 by n 2 into ZL minus DL. So this is our so I is equal to 1 is my data set, right? Here I run over a batch of n samples. So but then Z is my output from the nth layer. What I would actually want to compute is dou J by dou W. So I and J is one element in my nth layer in W capital L, right? So I have one element in this weight matrix. So I would want to compute this gradient with respect to each of my W's to see how it affects my final output. So this is done through chain rule. So all my so this Wij connects ith neuron in my previous layer, L minus 1th layer, to jth neuron in Lth layer. So only ZJL is affected by all these weights, right? So this is what the chain rule of differentiation gives. Are you following this? I'm sorry if you're not. Does this make, if you have any doubts, please ask me. So I need to compute this, right? I have already computed this. So I need to compute this here. That is dou Zj of L by dou Wij. So how do I compute this? What is Zj of L? It is sum of Wij into Zi of L minus 1. My I goes from 1 to number of layers in L minus 1. So I have L minus 1 in L minus 1 nodes here. This is my W1J, W2J, W in L minus 1J that goes to my jth node. This actually gives me YLJ, which again gives my ZLJ. It's actually f of this whole thing. So let me write this as Y. So Zj of L is f of Yj of L by applying chain rule here, and this Yj is a function of these W's here, right? So dou Zj of L divided by dou Wij of L. So this weight affects the final output only through this Yj of L, right? So this can be written as so what is this term here? It is actually f dash of Yj of L into but where do I want to plug this in? At the end, I want to compute dou j with respect to this particular weight. So this we got, the equation we got was dou j by this is usually abbreviated by dou delta j of L, because at every layer I would have to compute this. So if I represent it by dou j of L, and this will be this. So it's like I'm back tracing my error at every step. Wij of L affects my output of so the in my forward pass, the way I am progressing is this Zj of L, then it will go to my final computation of j. So if I have this step dou j by dou Zj of L, this will further affect me through y here. So I do dou Zj of L by dou Yj of L, then dou Yj of L by dou Wij of L. So this is the sequence of steps. This is how I backpropagate my error. Were you guys able to follow the intuition behind backpropagation?
Yes, ma'am.
Okay, I think I'll stop here then. So this is how I showed you how to compute this with respect to one weight in my entire network, right? So but then at every layer this is what you keep doing. So only the indexes for L plus 1 will change. So you start from the last layer. I first compute my deltas with respect to L minus 1th layer, then backpropagate it to the previous layer, and so on. So this is called the backward pass. So forward pass, I go from first to second to so on to end, and compute my error based on my cost function, and see how it affects each of my weight, and through the chain rule of differentiation I update the weights. So I update it using gradient descent. At k plus 1th instant is Wijl at kth instant minus I use some learning rate or the step eta and dou j by, so the direction in which I update this is to reduce my cost function. So this is the gradient descent algorithm, where these are computed through backpropagation. Any doubts on this? So there are I will share the link. I'll upload this video and share the link for some Python notebooks, so that does all these things. So you can see how it is actually implemented. Yeah, today's session it went on with writing the math of it, so I could not go over the code for it. I think you can attend the other two sessions where they'll discuss, go over the code notebook for this as well. I'll share the link for those anyway. I would suggest you guys to watch at least the first part of the week's lecture and come for the session from next week. Is that fine?
Yes, ma'am.
Okay, then if no one has any questions, we can end the session.
Thank you.
Okay, thank you everyone.
Thank you, ma'am.